Hello everyone. In this video I will explain translation lookaside buffer. Uh, TLB buffer, these are actually cache memory for page table. Uh, let's see this example, then it will be more clear to you. In our virtual memory, all virtual addresses are actually converted into physical address, and then that content stored on that address will be accessed. So whenever a virtual address is provided to memory management unit, it should provide a address and that data has to be accessed in single memory access. This is the view, this is the expression user is carrying. But what actually happens whenever a virtual address is provided to memory management unit, that first of all access the page table in order to find out the corresponding frame number, like in which frame number that page is stored. So this will be counted as first memory access because page table also stored in RAM. So whenever a virtual address has to be accessed, in order to fetch physical address for that virtual address, frame number has to be fetched, and in order to fetch that frame number for that corresponding page table has to be accessed. So in order to access that page table, we need to go to page table address in RAM, and it will be counted as first memory access. And after looking in that page table, if that page is available in RAM, the corresponding frame number will be achieved. Corresponding frame number will be fetched. And once this frame number fetched, the offset will be combined with frame number and the physical address then is accessed. So it will be counted as second memory access. So virtual address accessing actually involve two memory access. So in order to reduce this delay, translation look-aside buffers are used. These are actually cache memory. There are two types of cache memory. One is internal, which is inbuilt in CPU, and second one is external, which is not inbuilt in CPU, which is actually uh, on motherboard. So this is outside the CPU. So here we are considering a normal cache memory. So accessing a cache memory is very faster as compared to accessing RAM. So this cache memory is actually a table, and this table there are keys, there are value. So in keys, page number will be stored, and in value, frame number is stored. So let's assume we are having a virtual address 1101. This virtual address has to be accessed. So in order to access content of this address has to be converted into physical address, and then content stored on that address will be accessed. So whenever a virtual address is given, first of all this address page number. So if you can see, we are having first two bits for page number, because there are a total number of 4 pages, and in order to represent these 4 pages, 2 bits are required. So 2 bits are used for page number, and these 2 bits are used for offset. So these two page number will be checked in this cache memory. So let's say there are 10 entries in this TLB. So one property of this cache memory is that all entries will be checked at the same time. This is actually associative memory. So this address for 1101, page number 3, because 11 this is the decimal of 3, so page number 3 will be searched in this cache memory. Initially this cache memory is empty. So if a entry is not found in this translation look-aside buffer, this will be known as TLB miss. In case if that page number entry available in this TLB, that will be considered as a hit. So there is no page entry for 3, so it will be considered as a TLB miss. And whenever there is a TLB miss, next it will fetch page table. So now it will be so first of all check TLB for virtual page entry. So in case if entry found, it will be TLB hit, otherwise TLB miss. Second thing, in case of TLB miss, page table will be searched. So now it will search page table. So in page table also there is no entry for this page number, or we can say there will be one entry but that entry will be invalid. So here is, let's say, 0123, and this bit will be 0000 because no page available in RAM right now, so all pages are invalid. So that corresponding page also not available in page, this is known as page fault. So in result of page fault, the corresponding page number will be loaded in the memory. Now after loading that page in RAM, a corresponding entry will be created in page table that page number 3 is available in frame number 0 and the valid bit is 1. And after creating this entry, same entry will be written in cache memory as well. So this memory says that page number 3 available in 0 frame number. So now so after writing this entry in cache memory, the corresponding data will be fetched from this address 001. Now let's say in case of a page entry found in TLB, let's say we want to look for this page number 1110. So the page number of this page is 11, which is 3. So this number will be searched in, first of all, cache memory, and this cache memory will give frame number, and this frame number will be taken, this frame number is 0, and offset will be taken from here, which is 1 0. So in this case, in case of TLB hit, we will get corresponding frame number from this cache memory itself, and after getting this address we will directly go to that address. So in this case we are accessing RAM, so this entire we are representing as RAM. We are accessing RAM only one time. So whenever there is a TLB hit, RAM will be accessed only once, but in case if there is a TLB miss, there will be two memory access. So in order to reduce that delay which actually taken by two memory access, translation lookaside buffers are used. So translation lookaside buffer, this is a cache memory which actually stored recently accessed page entry. So whatever entry accessed recently, so there are this cache memory actually limited, so it can store only a limited number of page entry. In next lecture I will explain page replacement algorithm in memory management. Thanks for watching.